Hello everyone, welcome to the XGSLab tutorial. In this tutorial, we will step through the GSA FD module referencing the IEEE Standard 80. So you can see that we've already selected our project and selected the GSA FD module. Here on the start page, you can find some reference information from the tutorial documentation. Also, you can find the links to our YouTube, and you can find some more informational videos on our website. The reference for our DXF is available on the help desk area. So when we start our project, the first thing we'll want to do is go to our project information and enter in some of the characteristics about the site, such as available fault current, where resistivity measurements were performed, and the date of those. You can also incorporate the customer, designer, or the site location in the XGSLab project file. This allows you to actually export your model to Google Earth. Now, we're going to reference IEEE Standard 80, and we'll do that for the touch and step voltage calculations, the split factor calculation, and our conductor sizing. And because we're using the GSA FD module, we can specify the frequency that we'll evaluate our system at, which will use the 60 Hz power frequency. Next, we will select this multi-layer model icon. This allows us to either manually enter in a soil model if we know the characteristics of our environment, or we can go to the multi-layer group box on the left-hand side and hit the calculate next to this soil resistivity analyzer. I'll reduce this message bar at the bottom here to give us more space, and we can see by clicking on the figure icon that the A column represents the space between our voltage probes, and the C column represents the space between our voltage and current probe. This allows users to enter in either Wenner or Schlumberger resistivity measurements. With this tutorial, we'll just follow along and use the resistivity measurements provided in the tutorial documentation. Pasting those values from Excel into our table, we can see a preview of the resistivity measurements on the right. And using XGSLab, we can use the automatic detection tool to determine the number of soil layers, or we can force a number of soil layers, in this instance 2 layers, and the software will help determine the appropriate soil resistivity based off these measurements. There are also statistical tools such as averaging or weights that you can use to help evaluate your soil resistivity measurements and determine an appropriate soil model. Hitting the calculate, we see that we have a 2-layer model that's been calculated with a top layer of 53 ohm meters. That's about 1.28 meters thick, and a bottom layer of 29 ohm meters. We'll apply this, and we can see this is now populating our multi-layer model table. We can see the chart of our soil model by going to the results group box. And here we can take a snap of this image to be saved for our automated report. Now that we have a soil model, we can actually incorporate our grounding system layout. And there's a couple ways that you can do this with XGSLab. You can either draft a grounding system. So in this situation, first I need to set my conductor characteristics using the group box, the draw group box. And this is something that I'm going to be pulling from our conductor library, which will show us user customizable. So in this instance, I have a 4-aught conductor that I'm going to be placing at 1 meter depth into the soil. And I can go ahead and select my rectangular element to draft a rectangular grid. It's relatively common to incorporate ground rods in these systems, so we can do that by selecting a new type of conductor property and selecting my vertical element. And this ground rod is going to use the LV value, this vertical length, to insert a 3-meter long ground rod. Here you can see in my YZ view and my XZ view, we have that ground rod populated there. You can draft your whole grounding system this way, but following the tutorial, we're going to the import and export icon, and this allows us to import a grounding system from a CAD file. Here we have the DXF that's available from the help desk, and this represents the purple conductor shows our grounding system that we want to import. This blue conductor represents another network of conductors or a separate electrode that we want to also import and evaluate. So let's go ahead and do the importation process. First, you'll navigate to the directory that you've imported or saved your DXF from the help desk area. Next, we'll need to specify the scale of the drafting. And then we can start incorporating each layer that applies to our grounding system. So the IO1 layer represents that purple conductor, and we're going to use stranded conductor that's 70 millimeters squared. And I'll maintain the same tag name, but I want to shift those conductors 1 meter into the earth because the CAD program has that drawn at a z-coordinate of 0. Next, we'll want to incorporate that IO2 layer, and we want to assign a different electrode because that is the blue conductor that we saw, and it is a separate system. And we'll go ahead and force this 1 meter into the earth. And the next thing we want to incorporate is the rod 1 layer. But what we'll find is that the conductor that is referenced needs to be added to our conductor library. So we can do that by going to our conductor library, selecting the type of conductor that we want to incorporate. In this case, it's going to be a 20 millimeter diameter pipe with a thickness of 5 millimeters. We'll specify it's steel, and just as a placeholder, we'll put a cross-sectional area of 300 millimeters squared. We can get a more exact value using the calculator. So here we can enter the 20 millimeter diameter, adjust the thickness of this to 5 millimeters, and find the cross-sectional area of 235 millimeters squared. Saving this, I can now use that value for importing my grid. And you can also find that you can set your drafting to use the conductors from the library. You can see by that selection, I now have the draw tool using my 20 millimeter diameter conductor, or the pipe that I've just added. So let's go ahead and add that rod layer using the new conductor type, which is a pipe and 20 millimeters thick. We'll maintain the same tag definition, but I do need to shift this 1 meter into the earth. Now that that conductor is added, we want to add one more layer that's going to be just reference information. We want to understand where our drive path may be or some of the limits of our equipment, and we can add that as a background layer. So it's not going to affect our system analysis, but it will be visually displayed for our own user's reference. Importing this, you can see on the bottom left we have a connection settings tool and a gap length of 0.1. This is a tool that allows you to import a CAD program or a CAD file that may have some gaps on the corners or edges of conductors, and XGSLab can automatically connect those for you. Once we've imported our system, we can see that we have a list of conductors, and this list is user selectable or filterable, similar to an Excel sheet. But what we really want to see is the visual display of our system. And here we can see the grounding system. Here's where our substation is going to be located, and this is where we want to actually incorporate our fault. So here I will select a conductor, go to my conductor editor, and in the victim dropdown, I will insert the 26,930 amp fault that's available from our power system. I will also hit the debug, and this is just going to check that there are no errors in my importation, such as conductors overlapping, or if I assigned conductors to electrode 1 or electrode 2 and they were connected, it would flag those as errors in that electrode 1 and electrode 2 should be separate conductors. So we have a successful debug. I want to incorporate a couple more things before we actually compute our system. I am going to add a couple of reference points, and these are going to be references that we can use in our touch voltage calculations. So we have a reference point at this location and another reference point right at our entrance. Once we've added these reference points, we'll go ahead and calculate our system to determine the grounding system impedance. Now that our computation is completed, we have a new couple tabs. The analysis tab, we can go to our GPR and earthing icon here, and we can see a reference point 70E. And this is a reference that has our 26,930 amps injected. This is going to result in a ground potential rise, or a voltage potential of 2,160 volts, because our system impedance at that point is approximately 0.08 ohms. So just for better clarity in the future, we'll name this reference point our substation. And this is a part of the steel factory. It's still a part of that same, this is the second reference, or the first reference point we really added, the flag. It's still a part of the IO1 conductor network. And here is our entrance, which is the IO2 layer that we incorporated. And we can continue on looking at this system with the current fault current, but we want to actually incorporate a fault current split after we save these changes. We can go to our project tab, and in the split factor tool, we can use that 0.08 ohm impedance that we calculated using the 26,930 amp fault current with a 60 hertz power frequency, and assuming that clears in half a second. We also want to incorporate an X over R of 30. We can now determine the amount of fault current that is going to produce a ground potential rise at our system, and how much of that will actually take alternative paths, such as transmission line shield wires or distribution neutrals. There's a couple options when you're using the IEEE 80 split factor tool. You can either enter an equivalent reactance and resistance, or you can force a split factor. In this instance, we're going to follow the tutorial, assuming we have 2 transmission lines with shield wires and 2 distribution lines with neutrals. We can expect an impedance of 0.455 ohms for our resistance and our reactance of 0.24. Hitting calculate, we can see our actual grounding system will be experiencing 25,000 amps, or approximately 25,000 amps, producing a ground potential rise of our system. And I want to incorporate that in my design either through a factor, or I can go back to my draw and change my energization. Going to my victim dropdown, I'll change this to that 25,000 amp fault. Now this is going to require that I reanalyze or recompute my system. Before we do that, what we'll look at is the conductor size as well, making sure that that 70 millimeter cross-sectional area is sufficient to support the 26,000 amps that's going through our system. So we'll enter in that 26,930 amps. That has a clearing time of half a second. We can also look at other faults at the same time. So we can look at another fault occurring with 21,890 amps. and a identical clearing time. Now, because these are having the same clearing time, we know that the fusing is really going to be determined based off of this first current that we've entered. We'll want to incorporate this K factor as well. So if we're evaluating the ampacity of a single conductor lead from a piece of equipment to our grid, this K factor is going to be 1, indicating that all current must go through that lead. However, if it's already in the grid and we're looking at the current or ampacity of our grounding conductor that's buried, there will likely be 1, 2, or maybe 4 paths available for current to flow, and that allows us to reduce the total amount of current that we want to evaluate that conductor's ampacity. We'll use 0.6 following the tutorial. We'll select our copper material and calculate that we need a minimum of 40 millimeters squared in order to support the fault currents that we're seeing without the fusing of those conductors, which is great because we have that. We'll also want to calculate the touch and step voltage limits, and this is going to reference the IEEE standard for determining a permissible voltage that someone will be able to withstand. And we'll use a half-second clearing time for that. We'll need to debug once again and recompute. Now that our operation is completed, we can look at our GPR and earthing impedance once again. Here we can see we have 25,000 amps that we've injected, and our voltage on our system is 2044 volts. Our impedance of our system doesn't really change. We can now look at some of the electrical properties of our system. So if we want, we can see the current that's going through all of our conductors in our network. Here we can see a significant current going through these 2 leads that connect our substation to the rest of this factory. We can also take a look at our voltage potentials of our system. We can see that the highest voltage potentials are right where our fault occurs, and we can see significant drop off as we go across our system. And this voltage potential is really what's being propagated through the soil or transferred to this system through the soil. Performing a grounding system analysis, we will want to evaluate our touch and step voltages. So we can do that by calculating the Earth's surface potentials. Here we're going to the area calculation tool, and we are going to match the area that is specified in our tutorial documentation. We'll set a length of 480 and a width of 400, and we'll adjust the step length to be 3.5 and calculate. Now all of those little dots, those are points where XGSLab is specifically calculating the Earth's surface potential. And that's going to be used to determine what the voltage difference is between any piece of conductor and the Earth's surface where an individual will be standing on. And with that information, you're able to determine the touch voltage values. You're also able to compare the voltages between these points to determine the step voltage values. Once this completes, we'll also be able to plot our ground potential rise or visualize the voltage that's in the soil. So here our calculations completed, and I'm just going to display the ground potential rise or the earth potential rise. Here we can see we have a system display that's a 3-dimensional view of our fault in that substation, and we can see the voltage drop as we go farther and farther away from the energization point. We also want to evaluate our touch potential voltages, And we can do that using our safe areas plot. This is providing a green, yellow, and red indication. The green would indicate that we are meeting our touch and step voltage limits according to IEEE standard 80. Yellow represents that we're exceeding touch voltages, and red represents areas where we're exceeding touch and step voltages. And what we find is this site is exceeding the touch voltage limits. But my reference mode is set to a specific reference point. I can change my reference to use all of my available reference points, such as these two other flags. So now when we plot our safe areas, it's going to compare the Earth's surface potentials to our various reference points. And we can see a very different plot here. Another way to visualize this is using our elements. So instead of comparing to a specific reference point, we're going to start comparing the Earth's surface potentials to our components or our elements of every one of our conductors. And what we can see with this elements comparison, or using the elements reference, we are getting a more accurate view of the voltage difference between the equipment that's located next to the different spots where somebody may be standing and in contact with a piece of equipment. Now, these reference points are very useful, especially if you have a bus bar where things are centrally grounded and the ground connection is actually farther away. You can use this as a set reference to determine touch and step voltages, or really touch voltages in that situation. What we can see is that we're still exceeding our touch voltage limits, and we can correct that or mitigate that by incorporating a surfacing layer. So I'm going to my soil group box and incorporating an asphalt layer. And according to the tutorial, we'll just incorporate a 50 millimeter thick asphalt layer. When we're incorporating this, we do need to recalculate our touch and step voltages. And we can see a new permissible limit is provided with our surface covering layer. Applying this, going over to my touch and step voltage calculations, I can now see that my touch and step voltage group box includes this SCL checkbox. Here I can set my reference to all elements once again. And using the SCL, I am incorporating my asphalt layer. So when I plot my safe areas plot, we'll see compliance throughout. Now we can see there's compliance throughout our entire grounding system, and this is representative of the permissible limits associated with a asphalt layer. So we'll take a snap of this for our grounding system analysis or for our automated report. We can also incorporate a touch voltage plot. This touch voltage plot is, as you can see, it's removing that red, yellow, and green mask that we're using when we're comparing to our permissible limits. This is just the absolute magnitude of touch voltages. So we'll go ahead and take a snap of that as well for our report and plot the step voltages. Now that our step voltages have completed, we can take another snap of this. And when we go to our summary tab, we can find a gallery of all of the images that we have snapped going through this analysis. And this is going to be captured when we create our report. This report will have a table of contents and incorporates any of the information that you included in the project information. It provides the soil resistivity measurements and the soil model that you were using, as well as the energization and the limits are associated with your system's evaluation. Here we have our touch and step voltages, our touch voltage plot, our step voltage plot, and the conductor sizing calculations and split factor calculations, as well as a bill of materials. All of this is going to be exportable to a PDF, Word document, or other formats. It's important to note that this tutorial video is covering a small section of the tutorial that's available. So there's a lot more content that's available referencing the tutorial guides themselves. And we have more tutorials available on our website.